But the first thing, though, we kind of have to discuss is this thing called the kinetic molecular theory. And this is basically a model that's been developed that tries to explain why gases behave the unique ways that they do. So we have a few, kind of like some basic principles of this theory. And once you understand these little principles, then it kind of makes logical sense why gases behave the way they do in terms of like their pressure, their volume, their temperature, and things like that. So the first little postulate or the first little principle of the theory is that gases, of course, are small particles, and they are moving randomly with a high velocity. So that's the first thing. So we're assuming then that the gas particles here in this room, for example, the air molecules are not just sitting still. They are constantly moving, and they're bouncing all around, and they're going randomly and very quickly. In fact, they're actually traveling hundreds of miles per hour, typically. So that's the first thing. So they are moving, not just sitting still, hovering in place. And we're also going to assume that they have no kind of attraction between each other and no kind of repulsion between each other. Now there is, in fact, a little bit of attraction between them, but it's very minimal for the purposes of the theory to make it work nicely. We kind of assume there's none. And that kind of makes sense because most gases are going to be nonpolar, which means they're only going to have the weakest of forces anyway, which are dispersion forces. And they're moving super fast because they don't really have time to have much of an attraction as they're zipping by each other hundreds of miles per hour anyway. The next thing is that we are assuming, again, they are super tiny. We saw that in the last chapter or so, that atoms are so super tiny we need a giant number even to deal with like a real-world gram of something. So the volume of the atom compared to the volume of the room, let's say, or the container or the cylinder or whatever it is much smaller. The next one is we are assuming they are constantly moving, so they never kind of stop and slow down. And then we are assuming that the amount of kinetic energy, which again, remember, is the energy of motion they have, that is going to be proportional to the increase in their temperature. So we've seen that in the past, right? As things get warmer, they have more kinetic energy, which means they're typically going to move faster. As they get colder, they're going to move slower. So those are kind of like the 5 things to kind of file away in the back of your brain as we're thinking about gases and how they behave in terms of different properties. So they have particles that are moving randomly and quickly. They are not really drawn to each other, and they're not really like repelling each other. They have a really small size compared to whatever container they're in, the balloon or whatever. They're constantly moving, and their kinetic energy is proportional to their temperature. So that's kind of the 5 things we're going to think about here. So there are kind of 4 different ways we could try to measure a gas. The first way you can measure it is based off the pressure. Call that capital P. And I'll explain the pressure here in a second. But it's the force that gas is exerting as it's banging off the walls of the container or the sides of the balloon or whatever it is. The next one, capital V, is volume. And then capital T, whoops, sorry about that, which is temperature, which again we said is tied in with kinetic energy and how fast they're moving. And then the amount of the gas, and that is lowercase n. And that stands for typically the moles of the gas. So 4 variables we're going to look at: pressure, volume, temperature, and moles. And we're going to see how they kind of interrelate. How's pressure related to volume? How's pressure related to temperature? How's moles related to pressure? And all these different things, we're going to see the differences. So P, V, T, and N. And we'll get to some formulas here that'll kind of tie P and V together and P and T together, and all 4 of them together. We'll see all kinds of different little formulas here. Okay, got that? Temperature, so pressure, and I'll explain each of these in a second. So pressure, volume, temperature, and the amount, which could be typically the moles. Okay, so let's look at what is pressure. Well, again, like I said, pressure is basically, it's the force being exerted on the walls. So let's say, for example, we have the air in this room, right? And it's bouncing around, it's smacking off the walls and the ceiling and the people. Well, that's exerting a certain amount of what we call atmospheric pressure. It has a certain pressure it's exerting. So you can think of it then, let's say let's say it's this whiteboard here we're looking at, and this whiteboard then is the surface. Well, the gas particles are bouncing off this wall, right? They're bouncing off the walls and everything else. Well, as they're bouncing off the wall, that causes a certain pressure, right? When they push on the wall. So the pressure basically is that force being applied. So basically, pressure comes down to the force being applied over a certain area. So it's the force per area. If you're in physics, you would love that. It's force per area. So, force per area. So how much force is it banging off the wall, banging off your body, whatever? Okay. Well, again, why are they exerting that force? Because, again, they are small and they're constantly moving, right? So they're bouncing off and hitting everything, right? They're bouncing off, and those collisions are causing a certain amount of force. Okay. Now, how do we measure pressure? The most common unit we use in science is called the atmosphere, abbreviated ATM. And 1 atmosphere has been defined as the average pressure at sea level. So you go down to the beach on an average day, and the general pressure you feel in the air, that's about 1 atmosphere, 1 ATM. Okay, so that's one way of measuring that pressure, the amount of the force per area. So that force that you're feeling then on your skin, you don't really realize it because you're so used to it, but there is a pressure on your body. That pressure is about 1 atmosphere. Another common unit is called mmHg, which is just what you think, millimeters, and what's Hg? Mercury, millimeters of mercury. Now that comes from an Italian guy whose name was Torricelli. And what Torricelli did was he had a big bowl of mercury, and in this big bowl of mercury, he put a long glass tube in the bowl of mercury. And he found that on various days as he came in, the height of the mercury going up the tube was different. So first he wondered, why is the mercury going up the tube in the first place, and why is it different from day to day? And what he realized is, well, there has to be something pushing on the bowl of mercury to force it to go up the tube. Well, the thing pushing down was the air, right? It's the pressure of the air. It's the force being exerted by those particles slapping around and smacking on the top of the surface. And then on various days then, as the pressure was different, right? Changes, right? Of course, the weather changes. You have high pressure, low pressure. Well, it would push harder or less hard. So the height of that column from here, the top of the mercury, up to here was what he was measuring. So he measured it in millimeters of the mercury. So that's one way of measuring pressure, and that's probably kind of like the most standard way outside of like science directly is to use the height of a column of mercury. So for example, in our labs, you might have seen this thing on the wall. It's a real long glass tube hanging on the wall with metal caps. That actually is an old school barometer. And in that long glass column, if you look at it, you'll see there's a glass tube, and at the bottom of the tube is a big pool of mercury, and the mercury is going up the column. So literally, all you do is you measure the height of the column of mercury, and that's the pressure. Well, how does that relate back to atmospheres? Well, 1 atmosphere has been defined exactly, no sig figs, defined to be 760 millimeters of mercury. If you want to do that in inches, it's about 29.92 inches. If you want to convert that into English. So for example, if you watch the news tonight, watch the weather, they'll give the pressure outside. And so the pressure today was 30.18 inches of mercury, or something like that, typically. Something like that. So again, the pressure, they'll give it in inches of mercury, because we're in America and not in the metric system. Or if you go on your phone, pull the weather app, same thing, how the pressure, it'll probably say INHG, inches of mercury. It's the same thing. So there you go. Now you know where it comes from. Now, 1 millimeter mercury is also the same as what's called a torr, which again, is the name of this Italian guy, Torricelli. Sounds like a delicious pasta or something. Have a bowl of torricelli or something, but it's a Torricelli torr. So 1 atmosphere then is 760 torr also. So 1 atmosphere is 760 torr also. 1 atmosphere is 760 torr also. Everybody got that? So same thing. Millimeter mercury, same as a torr. Okay, so again, all that's measuring is what force is being applied to the walls of the container, to the sides of the balloon, to the whatever it is, the pressure's right the gas particle is smacking into. Well, there's lots of other ways of measuring pressure. We won't go into all of these. Probably though the one though that you're most common, the one though that you're most familiar with is PSI. Probably everybody's heard of PSI, and that is pounds per square inch. Again, it's force per area. The force in pounds per area per square inches. So how many pounds of pressure are you applying per square inch? PSI. So that's just another way of measuring, right, pressure. So like you see it on your car tires, right? So we're saying your car tires, your maximum pressure is 35 psi or whatever, or basketball, you play your basketball, psi. Okay. Well, there are again 3 ways we can affect that pressure, and it kind of goes back to the ones I told you about: volume, temperature, and amount of the gas. Because we'll see as the volume changes, that affects the pressure. As the temperature changes, that affects the pressure. As the number of moles or molecules changes, that affects the pressure. So all of those other variables I mentioned before are going to affect the pressure. So let's go through each of these and see, okay, how does volume affect it? How does temperature affect it? How does moles affect it? We'll go through each of these. Volume, temperature, and amount. V, T, and N. Slide there? Okay, I'll go back here. Okay, so let's think about it. So again, a gas is particles. They're constantly moving. They're bouncing around randomly, right? They're striking the walls of the container, whatever's going on. So how about the volume? How would the volume affect the pressure? So let's imagine, I'm going to draw a little picture here. There's already one kind of drawn in here, but I'll draw a different one. So let's say I have a container. Maybe it's like a little piston here or something, it's a little cylinder. So in here I have a whole bunch of gas particles. I'll make them red. So what happens? Those particles, they are bouncing around, right? And they're bouncing off the walls of the container, right? So they're bebopping, bounce off the walls, and that's just creating a certain pressure. Well, let's say then that I have this piston and I push it down, and the volume gets smaller. So let's think about that for a second. So same container, now I slide the piston down. So the particles haven't changed. They're still the same number of particles. But what's going to happen then? What's going to happen then to the number of collisions they're having with the walls and the sides of the container? You're going to have more collisions, right? So more collisions mean the pressure goes up, right? So you can see that as the volume decreases, the pressure must increase, right? Does that make sense? Let me make a note of that. Maybe I can get the pen off here. So you can increase the pressure as you decrease the volume, and vice versa. If you make the container a lot bigger, let's say you took it and you made it a much bigger container now, I don't know. So you really widen it up. But again, you don't change the amount of gas, same number of gas particles. Well, now they're much more spread out, right? And they won't be colliding with the walls as often, right? So you're going to have fewer collisions with the walls, so a lower force. So just the opposite. As you increase the volume, then you decrease the pressure, right? Make sense? Okay, awesome. Okay. How about temperature? Okay, so let's say I have a container here with some gas particles. I'll just use the one here that's already drawn. And I take it and I cool it off. Okay, so I don't know. So I take it and I put a bunch of ice around it, right? Draw a bunch of little ice cubes here. These little ice cubes. So I cool it off, right? So as I decrease the temperature, what's that cause the molecules to do? They're going to move slower. And if they're moving slower, what will that do then to the collisions happening with the walls? Yeah, so less collisions, right? So they're working on bang, now they're only hitting it less often because they're moving slower. So as you decrease the temperature, you're going to decrease the pressure, right? So those are directly related, right? So as you decrease the temperature, you can decrease the pressure. Let me get an eraser here. An eraser. Maybe I'll do them both the same way for pressure. Let's say if I increase the pressure, I'm going to increase the temperature, right? So it's opposite of what I did with the volume. Okay, well, and vice versa then, right? If I had that same container and I were to heat it up, all right, so I put a fire under it here, and I heat it up. Well, now if they get hotter, they're going to move faster, so they're going to collide with the walls more often. So, right, increase the temperature, you're going to increase the pressure, right? So, and then the next one, how about just the amount of the gas? Let's say I have a cylinder. It has 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules, or 9 moles, and then I suck out some of the gas. Now it only has 1, 2, 3, 6 moles. Well, what's that going to cause then with the collisions? Lower pressure, right? So fewer molecules means there's going to be fewer collisions with the container walls, so lower pressure. And then vice versa, if I were to have the container and were to pump in more gas, now I'll get more collisions, so I'll get a greater pressure. Awesome. All right, so you can see how all three of these are kind of tied in with pressure. Okay, so that's kind of the broad strokes. Now we'll kind of dive into each of these. So each of these has a certain relationship. The first one's named for a very famous English scientist named Sir Robert Boyle, and it's called Boyle's Law. And Boyle's Law basically studied the relationship between what we just discussed, pressure and volume. How are pressure and volume related? So we see then, right, they are inversely related, right? As one goes up, the other goes down, and vice versa. One goes down, the other goes up. So they are what are called inversely related. Okay? So pressure is related to the inverse of volume, in other words. And just a reminder, this little symbol, this little alpha, means proportional, in case you forgot that. Proportional. So they are inversely proportional to each other. Okay? Yeah, I have it there. Or you can do that way too. Either way, doesn't matter. So as one goes up, the other goes down. That's what we're saying. Boyle's Law. As one goes up, the other goes down. So you can do a whole math derivation. You don't need to write this down. You need to know this. But how are they proportional? I mean, is it directly 1-to-1, or what is it? So you could actually solve for this proportionality constant, figure out what it is. So you can imagine it. Just an important, just call it, okay, some kind of constant k we're going to call it, and then you could do a whole derivation thing. As pressure goes up, volume goes down, because this has to stay constant. If one goes up, the other one has to go down. So you can imagine doing a whole thing like this. So we call this in the end P1V1 equals P2V2. This is called Boyle's Law. So this says the pressure times the volume that you started with is equal to the pressure times the volume after you change one of these. So let's say it was, 1 atmosphere and 10 liters, and now it's 20 liters. So I changed the volume. Okay, so what's the new pressure at 20 liters? So case 1 versus case 2. So that is Boyle's Law. P1 V1 equals P2 V2. So this is Robert Boyle, Boyle's Law. So Boyle was kicking around in the 1600s around England. So I think I have a picture. Oh yes. So it's kind of an interesting picture I took. I think I mentioned before. Way back when way back. But this is actually some data that Robert Boyle gave at a presentation way back in 1661. Here you see. So this is the actual data. So when I was at this place in London called Royal Society, like I mentioned before, they have all these archives of all these people's writings. He left his writings, and this is his actual notebook. Somebody actually wrote down the data he gave in a presentation. So crazy, holding it in my hand from 1661. So there it is. There's pressure versus volume data. He was presenting at a little meeting of some scientists way back, right? So 350 years ago. So okay, so let's just try a problem using this equation. This is what's called Boyle's Law. So let's say I have a 1.5 liter sample exerting a pressure of 1650 millimeters of mercury. What's the pressure if I increase the volume now up to 7 liters? So it was 1.5 liters, and then I make the volume a lot bigger to 7 liters. So just in general, what should happen to the pressure if the volume goes up? The pressure should go down, we would think, right? Okay, so let's try it out. Let's write it down here and see. So our equation is P1 V1 equals P2 V2. So I know the initial volume was 1.5. The initial pressure was 1650. The final volume was 7. So which variable am I trying to find? P2, right? I want to find P2. So P2 is the one I need to kind of isolate. So if I want to get P2 by itself, what do? Divide both sides by V2, right? So P2 is going to come out equal to P1 V1 divided by V2, right? Exactly. Yeah, so there's a little bit of algebra here, this chapter. Okay, so we just plug in what we know. So what was P1? What was the initial pressure? 1650 millimeters of mercury. Okay, great. What was V1, the initial, the starting volume? 1.50 liters over V2? 7.00 liters. Okay, so what units are going to cancel here? The liters, right. And I'll be left with millimeters of mercury, which makes sense because I'm doing a pressure. So that's a unit of pressure. So let's grab our calculators. Let's punch that in there, see what we get here. 1650 times 1.5 divided by 7. Looks like 3 sig figs, 3 sig figs, 3 sig figs. So what'd you get? How many? 354, yeah, that's what I got, 354 with rounding. And again, the units that were left were millimeters of mercury. So again, does that number seem reasonable? Well, yeah, because you just told me if the volume got a lot bigger, the pressure should get a lot smaller, and it did. It went from 1600 down to 300. So it did. It got a lot smaller, so that makes sense. Okay, good. Okay. Well, let's try one more together here. Let's say I have 1 liter of gas. This one, by the way, is the first one on your handout. If you have your handout, you want to pull it out, save yourself some writing. Hopefully you have that. 1 liter of a gas at 1.25 atmospheres is compressed down to 473 milliliters. What is the new pressure of the gas? Okay, so let's write down Boyle's Law here. We know Boyle's Law. So P1 V1 equals P2 V2. So which variable am I going to solve for? P1, V1, P2, or V2? The new pressure, so P2, right? The new pressure. So same thing, we're going to rearrange, try and get P2 by itself, so it'll become P1, V1 over V2. But right now, what's the problem with this data? Why can't I just plug it in directly? Yeah, because one volume is in liters, one volume is in milliliters. So right now they won't cancel. So you have to either turn them both into liters or turn them both into milliliters. It won't matter which you do. As long as they're the same unit, then they can cancel. So I'll just turn them both into liters. So I'll turn V2, that was 473 milliliters. We'll turn that So milli, what's the prefix for milli? 10 to the negative 3 liters, right? So that would become 0.473 liters. Okay, there we go. So now we got volume 2 in liters. So let's plug in what we know here. P1, what's P1? 1.25. Okay. What's V1? 1.00 liters, good. And what's V2? We just found it, right? Okay, so now our units can cancel, right? Because now we've got liters and liters. Okay, so punch it in our calculator here. 1.25 times 1 divided by 0.473. How many sig figs should we have? Looks like about 3, so what is it? 2.64. That's what I got. Okay, so just real quick, does that number seem reasonable? Explain to me, does that seem like a reasonable number? I mean, kind of base. I mean, why? Why or why not?
The volume decreased?
Yeah, the volume went down about half, and the pressure went up about double. Does that make sense? You see that? Versus the volume was about half, so the pressure was about double. So one goes down, the other goes up. Right, so that makes sense. Okay, your turn. Try the next one here. So the highest pressure ever produced in the lab was about 2 million atmospheres. You know, so that's pretty big pressure. 2 million times the pressure you're currently feeling. If we have a 1.0 times 10 to the negative fifth liter sample of a gas at that pressure, then you take that gas out of that huge pressure and put it into a lower pressure of 0.275, how big would the volume swell up to? So figure that out. So what's V1, what's P1, what's V2, what's P2, right? Think about it. Rearrange your equation. Talk it over if you need to. See what you can come up with. So which volume are you talking about? It says a new volume. Which variable is that going to be?
V2.
You're going to solve for V2, right? Okay, so yeah, so rearrange your equation. First thing I would do is rearrange the equation. Make sure your units then are the same around, right? So all the pressures are the same unit, the volume is the same unit. If not, you got to convert it first. Talk it over with your neighbors, see what they got. See what you think. Talk it over, check your sig figs. Okay, let's hear an answer. What'd you get for the new volume? 73? People are saying 73? Okay, let's try it out here. So, Boyles Law equation, P1 V1 equals P2 V2. And you said we have to isolate V2, all right? So the way to do that, maybe I'll just show you the algebra one time. Divide both sides by P2, right? And that leaves you, V2 equals P1 V1 over P2, right? V2 equals P1 V1 over P2. Okay, so P1, that's the initial, the starting pressure. What was the starting pressure? 2.0 times 10 to the 6. atmospheres. Okay, good. V1.
1.0 times 10 to the negative 5th liters.
Yeah, so we have a huge pressure. Again, like I said, a huge pressure, 2 million atmospheres, and a super tiny volume, 100,000th of a liter. So it's not much of a gas at all, but it's under a huge pressure. And then we take that pressure away, and it goes to what's the new pressure?
275 atmospheres.
Okay. So make sure we cancel our units out. Which units are going to cancel? Atmospheres. We're going to be left with liters right there. Good. Okay, so 2 sig figs, you said it was 73. So again, so we had a volume of gas that was only, like I said, 100,000th of a liter, and it blew up to 73 liters. It got a lot bigger. Why is that? Because it was under a huge pressure, 2 million. Now it's only under 0.275 pressure, right? So yeah, it's a big difference. Okay. Let's try one more here. Who's ever been scuba diving? Anybody ever been scuba diving? Michaelin, that's it? One person? Okay, so here's a little scuba diving question for you. So there's this thing you can get called the bends when you're scuba diving. So you go down scuba diving for too long and you surface in really quickly. It's very dangerous at times, and it's called the bends. And basically what happens then is when you're down low in the water, well, the pressure is much greater because all the water pushing on you. Well, so all the gas in your body, all the nitrogen, oxygen dissolved up in your blood is under a high pressure. And if you surface suddenly and the pressure gets much less, well, what's the volume going to do? The volume's going to get expanded too. All these gas bubbles in your blood and your brain and your muscles begin to expand and pop and burst and cause all kinds of bad, nasty stuff. So, try this one out. So you have a diver, and the volume of gas in his blood is about 0.0825 liters, and the pressure at about 100 feet down is about 4 atmospheres. So it's about 4 times the pressure you normally feel. If he just quickly surfaces up to the surface where it's 1 atmosphere, what will the new volume of gas in his blood be? So figure it out. Okay, so let's write down Boyle's Law here. Again, so P1 V1 equals P2 V2. Which variable are we going to solve for? Yeah, what's the new volume going to be? So V2. So I rearrange, I divide both sides by P2, and I get P1 V1 over P2. Okay, so what's my initial pressure? 4.00 atmospheres. What was the initial volume?
0.0825 liters.
Thank you. And what was the final pressure after we got done? After he surfaced? 1.00 atmospheres. Okay, so we cancel out atmospheres. And you say it was 0.330. Okay, so yeah. So basically then what happened was the pressure got 4 times smaller, so all the volume of gas in his blood got 4 times bigger, which again would not be a good thing, right? So imagine all the gas in your blood dissolved up, like I said, in your arteries, your capillaries, in your brain, things like that, all just suddenly expands 4 times the size. That would not be a good thing typically, right? So you have lots of rupturing and hemorrhaging and bleeding of the brain, all that kind of stuff. So yeah, it's a very bad thing. So you have to go very, very slowly. Allow your body's pressure going to slowly adjust over time, and then the volume, will slowly, slowly increase, and you breathe some out, and increase, and you can breathe some out slowly. Okay, well, let's look at another one. Talks about Charles' Law. So Charles' Law relates volume and temperature. So this is actually Jacques Charles, but we'll call him Charles. He's a French guy. So he related volume and temperature. So we didn't really discuss volume and temperature directly. We discussed pressure and temperature, but same kind of deal. So let's say you have a container and you're going to maintain the same pressure. So you have a container like this and you heat it up. Well, you heat it up, particles begin to bounce around more, and they're going to push on the walls. So if they push on the walls, they're going to expand the walls. So the volume is going to increase as the temperature increases. It's like in a hot air balloon. Right? So you have a balloon, it's all flat, and you blow hot air into it. Well, the hot air bounces around, causes the volume to increase. That's Charles's law. Okay? So Charles's law basically says that as temperature increases, volume increases. So those are directly proportional. Unlike pressure and volume, which were inversely proportional, volume and temperature are directly proportional. So that's Charles. So you could do another whole derivation here where you figure out, okay, so how directly are they related? What is the proportionality constant? What's the ratio? You could do a whole thing. Again, I won't do it all. Oh, but one thing keep in mind, this is super important, which is why I underlined it. In gas problems, you have to always use temperature in Kelvin. Have to use temperature in Kelvin. Put that in big letters, underline it, highlight it, put a big star by it. Temperature has to be in Kelvin. And you might remember the nice thing about the Kelvin scale is 0 on the Kelvin scale is the absolute coldest possible temperature. There's no negative numbers on the Kelvin scale, which is why it's important to use the Kelvin scale. Because if not, use Celsius, you have a negative temperature, then you get negative volumes, which don't make any sense. You can't have negative volumes. So you got to use a scale here then that has no negative numbers so you don't get weird negative volumes. So please make a big note, highlight it, underline it, put a big star by them, but you got to use Kelvin for all of these. So anyway, like I said, you do a whole little math derivation, and you get a similar thing where the volume over the temperature to start with is equal to the volume over the temperature after you're done. So that's Charles's law. V1 over T1 equals V2 over T2. V1 over T1 equals V2 over T2. Okay. So let's just use his law a little bit here and try one out together. Let's say we have a big old helium balloon, 275 liters. You take it and you heat it from 20 degrees Celsius up to 40 degrees Celsius. I want to know what is the final volume at constant pressure, which means, again, we're only changing volume and temperature. The pressure is not changing. The pressure is constant. So I have an initial volume, an initial temperature, and a final temperature. I don't know what's the final volume. So this sometimes is a little harder to rearrange using algebra. So Charles's law, just write it down here again. V1 over T1 equals V2 over T2. So I want to find which a variable? V2. So how do I get V2 by itself? You can cross multiply. So basically what I can do, also what Roy said, is multiply both sides by T2, which is kind of like what you said too, cross multiplying. And these will go away, and then I'll be left with, okay, V2 is V1 over T1 times T2. Right? Okay, so let's plug in what we know here. So, what is V1? What was the initial volume we started with? 275 liters. T2 now. So T2 is which? 40 degrees Celsius, but has to be in Kelvin. So how do you convert Celsius to Kelvin? Add 273. So let's make a little note here. So T2, I'm going to take 40 Celsius. I'm going to add 273. And if you want to be really exact, you can have 273.15. But normally we don't need to be that exact. So about 313 Kelvin. So I'm going to put 313 Kelvin And T1 was 20 Celsius. So if I add 273 to that, I'll get 293 Kelvin, right? Okay. So 293 Kelvin. So Kelvin cancels, right? So let's try it out. 275 times 313 divided by 293. What'd you get? 294 liters. So the temperature went up a little tiny bit, and the volume went up a little tiny bit, right? Now remember, the big thing on that is got to use Kelvin, right? If you would have put Celsius, you would have put in 20 and 40, and that would have been double in the Celsius. You would have doubled the volume. That's not what it does. It only goes up a little tiny bit in Kelvin, so it goes up a little tiny bit in the volume. So make a note again if you have Kelvin, Kelvin, Kelvin. Got to use Kelvin. Okay. So pull out your hand out if you have it there. Let's try another one on here. Okay, so let's say you have a refrigerator at your house, and it's about 4 degrees Celsius in that refrigerator. Then you take a balloon that's initially at 22 degrees Celsius, and it has about a volume about a half a liter. And you put that balloon in the refrigerator. What will the volume of the balloon be once it's gone from 22 degrees down to the 4 degrees in the refrigerator? So, which variable are we solving for? V2. Okay, so let's write down our equation again. Charles's law is V1 over T1 equals V2 over T2. So we're going to try to get V2 by itself. So again, I'm going to cross multiply, and V2 is going to become V1 times T2 over, whoops, I wrote a T1 here. I mean T2, didn't I? Sorry about that. Must be T1 down here, sorry. T1. Yeah, so it's same as last time. Okay, let's plug in what we know. What's V1? 0.50 liters. What's T2? Yes, 22 Celsius, right. Add 273. 295 Kelvin, perfect, right. 295 Kelvin, good. What's T1? Right, 4 degrees Celsius plus 273. So 277 Kelvin. So 277 Kelvin. Okay, so Kelvin cancels. How many sig figs should we have here? Looks like 2. So what is it? What's the volume? Point what? Yes.
Temperature 2 is 4 degrees Celsius.
Everybody see that? So it started out, the balloon was at what temperature?
22.
The balloon was at 22, and I put it in the fridge that was at 4. Yes. So let's swap these. Try again here. Initially, it was at 22, and then it got in the fridge, it was at 20, it was at 4, so we're going to try that again. So, what goes on top now? Which one? 277. That sounds better. And 295 on the bottom. So, if the temperature goes down, the volume should also go down. Yes, that did not make sense. So, what is it really? Point what? 0.47 liters. Right. That makes more sense. Temperature went down, so the volume should go down because they're not moving as quickly, so they're not hitting the walls as often, so they're not pushing the walls out as often. much. Okay. Okay. Let's try this one. This one, for some reason, always gives students a little bit of trouble. I think it's because their algebra is a little rusty. So it says, how hot, so what temperature in other words, will a 2.3 liter balloon have to get to expand to a volume of 400 point liters? Assume that the initial temperature of the balloon is 25 degrees Celsius. So let me write Charles's law equation here. So which variable are we solving for? T2. So this is the one that students sometimes have trouble with. How do I isolate T2 when it's on the bottom like that? Yeah, you cross multiply. Remember this thing, cross multiplying? It's basically like you can take things and you can move them across the equal sign, but they have to go, if they're in the numerator, they go in the denominator. So they can move like this, or they can move like this. You cross multiply. Does that ring a bell? Sort of. So when you work this out, if I want to get T2 by itself, you got to put T2 up here on top, and then I gotta move the T1 from the bottom left to the top right. Got to move the V1 from the top left to the bottom right. And I wind up getting like that. If you're a little rusty on that, you're welcome to come see me. I can try to remind you how to do that little cross multiplying thing a little more in depth. Okay, so what do we plug in here? What's V2? 400 point liters. What's T1, the initial temperature? 298, right. So we're going to take the 25 Celsius and add 273. So 298 Kelvin. Good. And what's V1? What's the initial volume?
2.3.
Yes. So you're basically taking the volume and you want to make the balloon about 200 times bigger. So you're going to make it a lot bigger. You're going to have to make it a lot hotter, as we'll see. So what temperature do you wind up having to get out? 5.2 times 10 to the 4th Kelvin. So yes, you're going to have to heat it up to about 52,000 Kelvin, which would probably melt the balloon long before you got it that big, I'm sure. So awesome. Okay, you seem thrilled. Try C. A soda bottle is flexible enough that the volume of the bottle can change without opening it. If you have an empty soda bottle, which is a volume of 2 liters, so you have a 2 liter bottle at room temperature, and you put it in your freezer, and it's -4 in your freezer, what will the new volume of the 2 liter be? So you have a 2 liter, it's empty, you put it in your freezer, it's going to shrink, you know, but how much? What will the new volume be? Well, let's try it out here, see what the issue is. So V1 over T1. I'll give you these formulas, by the way. I'll give you Boyles Law, Charles Law, all of these. What will the new volume be? So which variable am I solving for? V2. I'm going to get V2 by itself. I'm going to multiply both sides by by T2. So V1, it was initially at 2.00 liters. T2, so it went down to -4 Celsius. So if I add 273 to that, now we are adding and subtracting. So far as sig figs go, you use the places. So 1's place plus 1's place goes to 269. 1's place. That's T2. 269. T1, it was initially at 25. Add 273, so we get 298 Kelvin. So what'd you get? 1.81? Did everybody get that? Okay, good. So yes, your 2 liter, go home and try it. Put 2 liter in your fridge. It'll shrink about 10%. It'll go. I'm sure you've all seen that, right? Put a bottle in the fridge, it goes, right? You know, it's all kind of, kind of crunches down, compresses. Charles's law. Now you know. Okay. Another law from another little French guy, Gay-Lussac. Gay-Lussac. Joseph Louis Gay-Lussac. So he discussed pressure and temperature. Well, not discussed, but he studied pressure and temperature. And the same thing, just the same way that if you increase temperature, you increase volume. If you increase temperature, you can also increase the pressure because, again, they're moving faster. It means they'll bounce off the walls harder, so you get more pressure. I'm getting the same thing. So pressure is proportional to temperature. So that's Gay-Lussac. So you could do a whole derivation. I won't write it all out, but some kind of a deal. P1 over T1 equals P2 over T2. And of course, temperature has to be in Kelvin, right? Anytime you're doing a gas law problem, always put it in Kelvin. So for the next week and a half, we're doing gases. Make sure you always put it into Kelvin. Okay, well, let's just try another basic one. I think we're kind of getting the hang of this. Mostly all it is just rearranging the equations and make sure the units are all the same so they cancel. There's not a whole lot to it. So let's try this one. A sample of gas at 3.00 times 10 to the third millimeters of mercury is inside a steel tank. So it's in a steel tank, which basically means its volume won't change. And it's cooled from 500.0 Celsius down to 0.00 Celsius. What is the final pressure of the gas in the steel tank? So I have temperature changing, and I want to find pressure. So P and T, that uses Gay-Lussac's law. So let's write in the equation here. So P1 over T1 equals P2 over T2. Right? So, which variable am I going to try to rearrange and solve for? The final pressure is P2. So we're going to multiply both sides by T2. So P2 is going to be P1, T2 over T1. What's P1? 3.00 times 10 to the third, right, millimeters of mercury. Awesome. T2. Don't think so. 270. Yeah, it went from 500 to 0. So 0 is the final one.
500 plus 273.
So T2 was 0.00. Now is the time, though, when you have a bunch of little decimal places, now is the time we need to use the more precise conversion that has decimal places. So I'm going to use that one. Remember the 1.5? So we'll use that one. Because we have decimals, we'll use the one that has decimals. So T2 comes out to be, 273.15. T1, it was at 500.0, 273.15, so 773, tens place and tens places, we'll go to 0.2 there, so 773.2 Kelvin. So Kelvins cancel. So the temperature went way down, which means the pressure should probably also go down. So did it? It was at around 3,000. What is it now? What is it? What's the number? 1,000 what?
I got 1,060, but I didn't use the .15.
1060.
Yeah, I didn't use the 273.15. I just used their 273.
Awesome.
5 to -3.
Yeah, it won't change it much. But okay. So, temperature went down, so pressure should go down, right? It's moving slower. I mean, just banging against the walls less often, so less pressure. Okay, let's try one more of these. Your turn. Try number 3. If you have a gas in a closed container, it's pressurized from 12 atmospheres up to 25 atmospheres. It was originally at 32 Celsius. What's the new temperature in Celsius? Notice it wants it in Celsius. So I have to do a little converting here. 362, 363, something like that. 640 Celsius? Oh, Kelvin. Yeah, this has to be Celsius. Celsius. I said that like 4 times. Don't forget, put it in Celsius. Put it back into Celsius. Okay. So P1 over T1 equals P2 over T2. We're finding T2, so we rearrange. And what do we get? P2 times T1 over P1? Is that right? That's right. Okay, so what's P2? What's P2? What's the pressure it went to? 25.0, I'm sure you meant to say. T1. .0. So I'm going to go ahead and use the 273.15 since the original number has decimals. So, yeah, 305.2, I guess, if I round officially to tenths place. And then P1, what was the initial pressure? 0.0, thank you. Okay, ATMs cancels. So what is it in Kelvin? What was it in Kelvin?
635.
Okay, I just heard like 3 different numbers there. What is it in Kelvin?
It's 635.
I heard 638, I heard 635, I heard... I got 636. So what do I do when so now I'm going to subtract 273, right, to get it back into Kelvin? I mean to Celsius. $363. Is that what you got? Roughly. Awesome. Okay. Let's do one last one here. Final pressure inside a scuba tank. So the scuba tank, it cools from 100 degrees, it's a really hot day, down to 25 degrees. How will the pressure change in the tank if the pressure was at 130 atmospheres? I'll pass back. The rest of the test. Oh, and I wound up not grading one of those naming ones that had the wrong formula. Somebody pointed out afterwards. So I marked through one of those, like, wait, it was long story, not long story, but it was like CD2, CO3, 3 or something like that. And so I just marked that one out, and I just didn't count that one. So the point, so it became, so yeah, the exam was worth 2 points less. Yeah, so I just didn't count that one. Because the original, I made like a measure made of chromium, but I changed it to cadmium, but I got to change the formula when I made it to cadmium. So. Like, people are like, what's going on here? And nobody said anything to me, so I didn't know. If you would have told me, I'd be like, oh yeah, sorry. You know, I just assumed you were crazy. But it was me. I was the crazy one. definitely had the wide gamut of grades. We had like near perfect percents, like 98, 99%, and then way down the other way too. So we had all over the place. So again, as always on this, you're gonna see this again on the final stuff. It's gonna keep building. If you have questions, come see me, my office. Go to the tutoring, right? Whatever you can do, right? Get some help. Like I said, maybe do your homework a little more frequently, a little earlier. Ask more questions. Whatever you need to do, right, to turn this around. If you weren't happy with the results you got, else you'll keep getting the same results. You can get the same way, get the same results. So. So what'd you get for this one? What's that final pressure in atmospheres? 104? Wrong one. Oh, sorry. Oh, that's the wrong one. Oh, let's add it backwards. Add it backwards there. Sorry about that. Okay, so let's work it out real quick. See what we got. So the final, calculate the final pressure. So P2, final pressure. So we got P1 over T1 equals P2 over T2. So final pressure would be P2. It's going to be P1 T2 over T1. P1, that's the initial pressure. So 130.0 atmospheres. T2, so that's the 25 and add 273.15. It's going to be 298.2, I guess. And then T1, 100. It's going to be 73 Kelvin. So what'd you get there? I'm sorry. Anybody? 104. Okay, so I think the next thing we'll do this next time, just because we're running a little low on time to kind of jump into it. But I want to discuss something called the combined gas law. We're going to put them all together, and then you can combine volume, pressure, and temperature all at the same time. And it's very easy, but we'll put that together. Yeah.
The grade written on the exam, like on page 2 or 3, whatever, like at the top, is that the whole exam, including the
No.
Scantron? It's just for the written part?
It is the written part, and the Scantron is always, it's that times 2, so because they're 2 points each. So I guess it was out of like 30 plus whatever that was, so it was out of like 87 or 89 or something like that. So. Okay, so one last little reminder before we head out a few minutes early. Remember, your science fair stuff is due, I think next Wednesday is the last day to turn it in over there if you haven't yet. So yes, make sure that make sure then that you and your group have your project worked out and you agreed on it and you clear it with me between now and Wednesday. And she also asked that you demo it for me before you do, which means that'll have to be next week in lab is the last. Well, I guess it'll be next week or the next week. So either next Tuesday you can bring it up to lab and show it to me, and lab at the very end, or the following Tuesday you can bring a little setup and show it to me. I'll pretend I'm a 6-year-old, and I will ask you questions, see if you can explain it in very basic lingo. So, okay, so enjoy your weekend. Start the homework. Do not wait to the end. Recipe for disaster if you wait to the end. Regular practice. So, okay. See you next week.